Now, welcome to the next session of the subject Engineering Mathematics. We were in chapter 3, that is discussing differential calculus of calculus. The concept is continuity followed by differentiability, right? Now, in the last session, we have seen examples of continuous functions over closed interval a comma b, polynomial expressions, sine function, cos, exponential, modulus of x minus k, etc. All these are continuous in all closed intervals a comma b. Now, even we have discussed one point. If f of x is not continuous at least one point in closed interval a comma b, then the function is not continuous in closed interval a comma b, and that point is called discontinuity point of f of x in that interval. Right? Now, let us give an example. One general example. Suppose if I have a function like this. This is coordinate system. Suppose we were discussing continuity in closed interval 1 comma 2. Suppose the graph is like this. Now you can see at this point there is some gap. Assume that this point is, for example, 1.8. Therefore the function has a break at this point, and luckily this point belongs to this interval. So therefore at this point the function has a break. Because of this simple failure also, only one discontinuity point, still we say that it is not continuous in this interval, right? Now I give one specific example where the function has a multiple number of discontinuous points. The example is this: f of x equal to step x. Basically this is nothing but integral part of x. This is nothing but integral part of x. How to define this? Let us start with some examples. Suppose integral part of 2, this is 2. I am saying that integral part. So 2 is an integer value, that's why square bracket of 2 is 2. Basically this is read as integral part of x. X can be any number. So if x is 2, then its integral part is 2. Suppose integral part of 2.3. This 2.3 I can write it as square bracket of 2 plus 0.3. Now this is my integer part and this is the decimal part. So its value is 2. So the difficulty comes when I take negative real numbers. If I want integral part of minus 2.3, and this is not minus 2. Now this value is actually minus 3. Let me explain how it is. When you consider x-axis, now this is, for example, minus 2, minus 3, this is minus 1, origin 1, etc. So come to negative direction like this. Now let us see. Here I want integral part of minus 2.3. For example, this is minus 2.3. Now I want integral part of minus 2.3. So consider all integers less than minus 2.3. So these are the integers less than minus 2.3. So what are integers less than minus 2.3? Minus 3, minus 4, minus 5, etc. All these are integers less than minus 2.3. Among all these integers less than minus 2.3, this minus 3 is the largest integer value. Therefore, integral part of minus 2.3 is minus 3. So how to define this? It is defined as the largest integer value which does not exceed x. Suppose when you come to integral part of 2, it is 2 only. What are integers less than 2? Integers less than 2 are less than or equal to 2. Integers less than or equal to 2 are 2, 1, 0, minus 1, minus 2, etc. Among all these integers, 2 is the largest value. So here equality is important. Here also equality works, but this is not an integer value. So therefore, the integral part of x is defined as, if x is a real number, the integral part of x is defined as the largest integer which is less than or equal to x. The largest integer which is less than or equal to x. Now let us try to draw the graph of this function at first. So when I try to draw the graph of this function in any interval, let us see where I get difficulty. X-axis, y-axis. So the function is integral part of x. Let us discuss its continuity in closed interval, for example 2 comma 4. Start from this. This is 1, this is 2, 3 and this is 4. So this is 1 on x-axis, y-axis 2, 3 and this is 4. Now let us draw the graph from 2 to 4 onwards. 2 to 3. Integral part of 2 is 2. So locate this. Integral part of 2.1, 2.2, 2.3 up to 3 the graph is 2. But when it reaches to 3, before 3 the graph is a straight line parallel to x-axis. When it reaches to 3, it jumps to this location. So from 3 to 4, integral part of 3, 3. 3.1, 3 only. Up to 4 it will be 3. But it reaches to, when it reaches to 4, it jumps to this position. Now we can see from 2 to 3, no issues. At the point 3, the graph jumps from this place to this place. So jumping has been taken place at this place and at this place. Therefore, in this case, 3 is a discontinuity point and 4 is a discontinuity point. So 3 comma 4 are discontinuity points of 3 comma 4 are discontinuity points of integral part of x in closed interval 2 comma 4. So whenever there is at least one discontinuous point is in that interval, the function is not continuous. So basically this is called a step function because the graph is just like steps of a building. That's why it is also named as a step function. It is also named as a step function because its graph looks like steps of a building. So first let us take this example. F of x equal to step x. Let us draw the graph of this function in this interval and write this conclusion. And even you can write this. You can have these examples. So you write the definition of this integral part of x just as a note, as a definition. You can write it as a note. If x is a real number, then integral part of x is defined as, if x is a real number, then integral part of x is defined as the largest integer less than or equal to x. If x is a real number, then integral part of x is defined as the largest integer less than or equal to x. The largest integer less than or equal to x. Next we discuss properties of continuous functions. Let us see what are these properties. Suppose I have a complicated function. I need to discuss its continuity in some closed interval a comma b. If I unable to draw the graph of that function, or if I unable to find the limit of that function at some points, then my job is very complicated. My task becomes very complicated. So in that case, if I try to apply properties of continuous functions, it may be some simple issue to discuss its continuity. Okay, so let us see. Suppose we have two functions, f of x comma g of x. Assume that both are continuous at a point A. Both are continuous at a point A. Then in that case, their sum is also continuous. That is f of x plus g of x is also continuous at the same point A. Is also continuous at A. So f of x and g of x both are continuous at point A. Then when you combine these using plus, I will get a new function. Even its graph is also continuous at the same point A. Now replace plus by minus. So f of x minus g of x is also continuous at the same point. Now replace minus by dot. So f of x dot g of x is also continuous at the same point. But when you look at the ratio, so we get different results. F of x by g of x may or may not be continuous at the point A. So ratio may or may not be continuous at that point. That means in some cases ratio is still continuous, in some cases ratio is not continuous. When it is continuous, when it is not continuous, I will tell you one example. Suppose f of x is a constant function 1, g of x is a constant function 2. So that is f of x is a constant function 1, g of x is a constant function 2. Suppose I am taking a value 3. We know that all constant functions are continuous at all points. So in particular these two are continuous at 3 also. Even when you take its ratio, that is f of x by g of x, it becomes a constant expression. Even this is also continuous at the same point. But I don't want positive examples. I want to say the result is negative. So one simple example is for me in the negative direction. So in the negative direction, the best example is this: f of x equal to 1 and g of x equal to x. Now this is a constant expression. This is a polynomial expression. So both are continuous at a equal to 0. But when you look at f of x by g of x, this gives 1 by x, which is not continuous at the point 0. So this is not continuous at 0. Why it is not continuous at 0? When you draw the graph of the function 1 by x, it will be like this. So it will be divided into two parts. No connectivity at the point 0. No connectivity. Or in simple words, 1 by x has no meaning when x is 0. When a function is not defined at 0, why should we discuss its continuity? Ultimately, won't get continuous, right? See, for example, if I am not a student, then can you ask me, are you continuous to the college as a student? You can't ask me. The same case applicable here also. So when a function has not defined at some particular point, ultimately it is not continuous. So here f of x is a constant function 1, g of x is x. Both are alone continuous at 0, but when you combine them using ratio, f of x by g of x, that is 1 by x, is not continuous at 0. But sub plus is always continuous, minus is always continuous, dot is continuous, but ratio need not be continuous. So by using point property 1, property 2, property 3, even you can, if you give me very complicated example, I can easily say whether it is continuous or not. Okay, note these points. Let f of x comma g of x, let f of x comma g of x be two continuous functions at a point A. Be two continuous functions at a point A. Let f of x comma g of x be two continuous functions at a point A. Then write all these properties. But regarding fourth example, to take this negative example, this is not at all useful. To give clarification, I wrote this example, but this is not required. Okay, just you write this example for negative case. It is not required for us. Next, we discuss the concept differentiability. Now, before going to differentiability, let me discuss what we do in case of differentiability. Previously, we have seen continuity of a function at a single point, and then continuity of a function in closed interval a comma b, and then properties of continuous functions. The same issues we can discuss even for a new concept, that is the differentiability of a function at single point followed by closed interval a comma b, and then properties of differentiable functions, right? Differentiability of a function at a single point, and then differentiability of a function in closed interval a comma b, followed by properties of differentiable functions, and then we compare the relation between differentiable and continuous functions. Okay, let us see. Suppose we have a function f of x and a is a real number. We say that f of x is differentiable. We say that f of x is differentiable at a if limit x tends to a, f of x minus f of a divided by x minus a exists. Exists means it is a finite number. Always remember one point, whenever we discuss the term exists in math class, it refers to finite number, right? See, this is very important for us. Limit x tends to a, f of x minus f of a by x minus a exists. And this particular limit is denoted by f dash of a. So this is what derivative of f at a. This is nothing but derivative of f at the point a. Now let us see. Generally, whenever we discuss derivative, we have one notation. Always we follow this notation, dy by dx. So this is nothing but change in y by change in x. Now in this case, what is my function? My function is y equal to f of x. Now what is change in y? This is f of x minus f of a. So y value at x only. Y value at a. Difference in y values divided by difference in x values. So derivative means dy by dx. There we are using the notation f dash of a. General notation is dy by dx. So change in y divided by change in x. What is my function? Y equal to f of x. So this difference gives change in y values, f of x minus f of a divided by x minus a. So therefore here when you look at this denominator expression, this is the change difference in x values and this is the difference in y values. Because we were discussing derivative at a, so find the limit of this function at a. So whenever limit x tends to a, f of x minus f of a by x minus a exists, then we say that f of x is differentiable at a and this limit is denoted by f dash of a. What it stands for? Derivative of f at a. So therefore, look at the beautiness. We have expressed derivative of a function at a point in terms of limits. And earlier we have seen continuity of a function at a point in terms of limits. That's why we have started differential calculus chapter with the definition of limit. The definition of limit may not be asked in any competitive examination. But when you go to PSU interviews, they may ask you, can you define limit of a function in terms of epsilon delta notation? Then people may feel a lot of issues. But always people can understand how to evaluate limits, how to prove that a function is continuous, how to verify a function is differentiable at a point or not. These things can be done by any people, but concepts are very powerful. So once you are able to identify all properties, definitions, etc., I think subject is not at all a big issue. So always try to focus, try to understand that basic definitions, properties, examples. They define subject very clearly, right? So therefore, derivative of a function at a point is defined in terms of limits. Note this. Let f of x be any function. Let f of x be any function and a be any real number. And a be any real number. Let f of x be any function and a be any real number. We say that f of x is differentiable at a. We say that f of x is differentiable at a if limit x tends to a, f of x minus f of a by x minus a exists. If limit x tends to a, f of x minus f of a by x minus a exists and f dash of a equal to this and f dash of a equal to this. Limit x tends to a, f of x minus f of a by x minus a, right? Now we discuss left hand and right hand derivatives, because when we discuss limits we need to discuss 2 points. One is left side approach, other is right side approach. Because the derivative is expressed in terms of limits, we need to go for left side derivative as well as right hand derivative. So the next concept is left hand and right hand derivatives. Next concept, left hand and right hand derivatives. Let us see what is LHD. The notation of LHD is f dash of a minus. As we mentioned earlier, a minus means we are approaching a from left side. So this is the notation for LHD, and this is given by limit extends to a minus f of x minus f of a divided by x minus a. Now how to evaluate this limit? Let us see. As x tends to a minus means x value is less than a. Now simplify the function f of x when x less than a. Simplify f of x when x less than a. Already f of a is some constant expression. You need not simplify x minus a. It is already in simplified form. This is a simplified version. Only thing is you need to worry about this f of x. So simplify f of x when x less than a. Once f of x is simplified, when x less than a, replace x by the number a only. Just like LHL value. Next one is RHD, right hand derivative. This is denoted by f dash of a plus, and this is given by limit extends to a plus f of x minus f of a divided by x minus a. Same definition, but a minus is replaced by a plus. So here extends to a plus means x values are greater than a. Now how to evaluate this RHD? Simplify the function f of x when x is greater than a. Once f of x is simplified when x is greater than a, replace x by the number a only. Right. Now my calculations are over. LHD is over, RHD is over. Now compare this. Suppose if LHD is a finite number L, RHD equal to a finite number K. That is LHD equal to L, comma RHD equal to K, where L comma K are finite numbers, where L comma K are finite numbers, and L equal to K, and L equal to K. Then f of x is differentiable at A, then f of x is differentiable at A, and f dash of A equal to common value. I can write either L or K because both are same. So whenever LHD equal to a finite number L, RHD equal to a finite number K, and L value, K value both are same, then f of x is differentiable at the point A, and derivative of f at A equal to L. Okay, so note these points. Now we discuss two important cases where function has no derivative at a point. One case is this. Suppose LHD equal to L, RHD equal to K, where L comma K are finite numbers, and L not equal to K. That implies f of x is not differentiable. This is one case. F of x is not differentiable at that point. This is one possible case. Another possible case is if either LHD or RHD, if either LHD or RHD is not a finite number, then also f of x is not differentiable at that point. F of x is not differentiable. So these are the two possible cases where function is not differentiable. Okay, note this point. Just these points are just like left hand and right hand limits. Okay, note these points. First one is f of x equal to, basic example, x square plus 1. Let us take a value 3. Now here what is f dash of x? Derivative of this function. We can go for direct derivative. This is 2x. Now replace x by a. So here f dash of a equal to f dash of 3 equal to 6. Now this is a finite number. Therefore f of x equal to x square is differentiable at 3. f of x equal to x square is differentiable at 3 because its derivative is 2x. We were discussing differentiability of a function at this point 3. So replace x by the point. So f dash of 3 is 6. 6 is a finite number. Since f dash of x a is a finite number, so it is differentiable at 3. Next, f of x equal to, for example, e power x. We will discuss its derivative at minus 2. Now, what is the derivative of f? E power x only. Now, replace x by a. F dash of a equal to f dash of minus 2. This is e power minus 2. This is 1 by e square, which is a finite number. Therefore, this e power x is also differentiable at minus 2. Therefore, e power x is differentiable at 2. Minus 2. Even at 2 also you will get, but to show the variation here, we have taken minus 2. Now let us take example 3. F of x equal to constant function minus 9. Take a value, for example 5. Now it is a constant function. Derivative of constant is 0. So here f dash of a. This is nothing but f dash of 5, and this is a constant expression. It is a finite number. This is a finite number. Therefore, f of x equal to minus 9 is differentiable at 5. Now let us take f of x equal to sin x at x equal to, or for example at a equal to, for example, pi by 2. So what is the derivative of sin x? This is cos x. Now replace x by a. Here a value is pi by 2. So this is cos 90 degrees. This value is 0. It is finite. Therefore, sin x is differentiable at pi by 2. Now as a last example, we take cos x. F of x equal to cos x at x equal to, for example, pi. Now what is f dash of x? Minus sin x. So we were discussing derivative at x equal to pi. Here I am using notation a. Both are same. So therefore here f dash of pi equal to minus sin pi. So sin pi is 0. It is a finite number. Therefore, interestingly, when you look at all these examples, what are the examples we have seen for different continuous functions? The same examples we have seen for derivative also, but we have missed one function, that is the modulus of x minus k, and that makes real that gives real beautiness to the calculus. Okay, we discuss after these examples, but for the time being, when you follow all these, all polynomial expressions, exponential function, constant function like this, sine function, constant function, all these are differentiable at all points, because when you replace x by any number, 2 into any number is always finite. When you replace x by any number, it gives finite number. So replace x by any number, it's a finite number. Replace x by any number, it gives a finite number. Similarly, in this expression, when you write x value, any value, then you will get some finite number. Therefore, all polynomial expressions, e power x, sine function, cos and e power x are differentiable at all points in the entire x-axis. Okay. So note all these examples. After this, we go for modulus of x minus k. Now, as a last example, we discuss modulus of x minus k by taking specific values of k. Suppose f of x equal to modulus of x minus 3. Now, let us discuss its derivative at 3. We concentrate on f dash of 3. So, here it is in the form modulus of x minus k. It is in the form modulus of x minus k, where k value is 3. That's why we discuss its derivative at 3. Since the function contains modulus operator, when you are discussing derivative, Try to evaluate both LHD and RHD, left hand and right hand derivatives, as we have seen in case of limits. Okay. Now let us see at first. LHD equal to f dash of 3 minus, this is equal to limit extends to 3 minus f of x minus f of 3 divided by x minus 3. Just this is the definition of LHD. Here extends to 3 minus means x value is less than 3. This implies x minus 3 is negative. Implies modulus of x minus 3 is minus of x minus 3. Therefore, this LHD equal to limit extends to 3. Now this f of x means this modulus of x minus 3. But this is simplified to minus of x minus 3 minus what is f of 3? Modulus of 3 minus 3, it is 0. Denominator is x minus 3. Therefore, this LHD is minus 1. Now this is a constant value which is minus 1. Now let us calculate RHD value. This RHD equal to f dash of 3 plus. This is nothing but limit extends to 3 plus f of x minus f of 3 divided by x minus 3. Now here extends to 3 plus means x values are greater than 3. When x is greater than 3, x minus 3 is positive. Now its modulus is, it is a positive expression, so its modulus is itself. Therefore, the function f of x is simplified to x minus 3. Therefore, this RHD equal to limit extends to 3. F of x is x minus 3 minus this f of 3 is 0 divided by x minus 3. Now this is 1. Now when you look at this, RHD equal to plus 1 and LHD equal to minus 1. So here both are finite numbers, but LHD is not equal to RHD. Both are finite numbers, but they are different numbers. Therefore, f of x is not differentiable at 3. F of x is not differentiable at 3. So this is very, very important. So note down these points. Now let us see whether this function is not differentiable only at 3 or at different points. Here the function is f of x equal to mod x minus 3. Just now we proved that it has no derivative at 3. My question is it differentiable at a point other than 3? For example 2. Let us see. Here f dash of x is modulus of x minus 2 by x minus 2. So therefore it is 3. So the expression is modulus of x minus 3 by x minus 3. Now when you replace x by 2, we get a number that is a finite number. Replace x by 2, this gives minus 1. Suppose if you want f dash of 4, it gives 1. Therefore, when you take f of x equal to modulus of x minus 3, if I want derivative at all points except at 3, I am getting derivatives like this. As we've seen, all left hand derivatives, if x is less than 3, derivative is minus 1. If x is above 3, derivative is plus 1. So therefore, the function has a derivative at all points except at 3. Therefore, the conclusion is, whenever we discuss a function f of x equal to modulus of x minus k, where k is any real number, then it is differentiable at all points except at k. So modulus of x minus k is differentiable at all points except at k. Note. F of x equal to modulus of x minus k. F of x equal to modulus of x minus k is differentiable at all points except at k. Is differentiable at all points except at k, because because f dash of x equal to modulus of x minus k by x minus k, because f dash of x equal to mod x minus k by x minus k, which is finite for all x not equal to k, which is finite for all x not equal to k. So this is the reason why it is differentiable at all points except at k, right? Now we discuss differentiability of a function in closed interval a comma b. Next one, differentiability in a closed interval or an interval. Differentiability in an interval, just like continuity in an interval. Suppose we have a function f of x, which is defined in closed interval a comma b. We say that f of x is differentiable in this interval if f of x is differentiable, if f of x is differentiable at all points of closed interval a comma b. That is, what is the meaning of this? F dash of x is finite for all x belong to closed interval a comma b. So whenever a function satisfies the condition in closed interval a comma b, then we say that f of x is differentiable in closed interval a comma b. Earlier we have seen differentiability of a function at a single point. Now we were discussing differentiability of a function in closed interval, bigger set. So find the derivative of this function, general derivative. Replace x by all points of this. So if f dash of x is finite for all x belong to closed interval a comma b, then we say that f of x is differentiable in this interval. Okay, note this point. A function f of x is said to be differentiable. A function f of x is said to be differentiable in closed interval a comma b. A function f of x is said to be differentiable in closed interval a comma b if f of x is differentiable at all points of closed interval a comma b. If f of x is differentiable at all points of closed interval a comma b, that is, f dash of x is finite for all x belong to this. That is, f dash of x is finite for all x belong to closed interval a comma b. Now earlier we have seen varieties of examples. Let me discuss one example. Suppose f of x equal to, for example, e power x, or I start with simple constant function f of x equal to 3 in closed interval minus 2 comma 5. Let us see the derivative of this function in this interval. Here what is f dash of x? It is 0. So f dash of x is 0 for all x belong to closed interval minus 2 comma 5. This is the symbol we use for all. Anyhow, we know that 0 is a finite number. So replace x by any element in this interval, we get 0. It's a finite number. Therefore, constant function is differentiable in this interval. Therefore, f of x is differentiable in closed interval minus 2 comma 5. Note this example 1.